So I can start with the seminar, and Jan-Peter, you can introduce yourself.
Oh, okay. Yes, for all who don't know me, I'm Jan-Peter. I work in the observatory, in the remote sensing group, and I'm basically a forest ecologist that is trying to use remotely sensed resources for research and analysis. Should I continue, or do you want to say something more?
I would perhaps say that everybody can write the questions already into the chat during the presentation, and it is possible.
And they can also interrupt me with the microphone if they want. No problem.
Yeah, most of people have joined without the microphone, so most of people are only able to write questions in the chat. But you can start with the presentation.
Okay, I see that's quite a small group today. I guess that most of the people are outside in the garden. I hope that the sound and everything is okay. If not, then please just let me know, and I will start. So I'm talking a little bit about primary productivity that is gathered from remotely sensed resources, and how this data can be utilized for ecological modeling, in particular for short-term weather fluctuations like drought. And this will be the first part. So I talk about two different kind of MODIs land products. And in the second part, I will talk about tree mortality, where we rather look from below, actually, into the grounds, because this is crown vitality survey data from the Icp Forest Network. And in both parts, I will show you some illustrative examples how this data can be utilized. In the second part, I will talk about the very prominent tree disease, ash dieback, which is currently spreading across Europe and killing most of the ash trees. And I will show some illustrative examples on how this Icp Forest Network data can be employed for monitoring. Oh, sorry, I have to press here. Yes, this is just to say all the data I show you here is part of this project, How Dry is Too Dry, which is financed by the Mobilitas Plus program of the Estonian Research Agency. And we started in November 2020, which means that we are still in the beginning, in an infantile stage of the project. So what I show you are certainly preliminary results, and yes. So why is this topic important? Rather than showing some pictures from the newspapers or whatever, I just show you these two plots here, which I got this morning from the European Drought Observatory, just to show you that the topic drought is quite actual around the globe, but also in Europe and also Northern Europe. When you see actually these brown, yellow areas, which are shown here on the map, on the right side, I zoomed in a little bit in the Baltic states, where you can see all this yellow area is actually area where we have currently, so this is the first 10-day period of April 2021, a very severe rainfall deficit. Then we already have some extreme soil moisture anomaly, which is this brown area here. And we have also in Estonia, here somewhere in Setomaa, you can see is a small red dot. We already have vegetation that is suffering from drought, and it's somehow mid of April, so a little bit unexpected for the northern countries. But what we are approaching at the moment is a nice spring drought in the Baltic states. So it depends a little bit on the next days what will happen. For Saturday, Sunday, they forecasted a little bit of rain, but not much actually. In particular, the area where I am living here in southern Estonia, they forecasted about 5 millimeters, which is basically nothing. And we have quite high temperatures since some days. And this data here refers to the first 10-day period. So it's not up to date because it takes a little bit until the latest data is processed. So I'm quite sure that we will have a nice little spring drought in some days. And this topic is also, so it's not the first drought that is appearing at the moment. Here I gathered mainly the same data from the European Drought Observatory for Estonia for 3 consecutive years, 17, 18, and 19. And 17 is for comparison because it was a very average year with smooth conditions. But 18 and 19 was exceptionally dry in Estonia, especially 18, because this was a millennial drought occurring over large parts of northern Europe. But then in 19, also in the northeastern parts, we had again extreme conditions. So this dark brown area is -2 standard deviations below the long-term average, which certainly have consequences for vegetation, in particular for forests. So the first questions we had actually before we thought about what kind of data resource to use for our modeling stuff was that MODIS provides a lot of information, a lot of different quantities that one can use. But the question is always which of them would be most suitable for estimating like productivity. As you may or may not know, is like this NDVI is a very common resource for showing vegetation stress from remotely sensed resources. But NDVI is from, let's say, from a biophysical viewpoint, NDVI is rather meaningless. It's unitless. I cannot say, well, is this yellow or brown value somehow translating into loss of carbon or not? It's just a relative value, so I cannot really use it for saying anything about biophysical properties. So we were looking for one which has a meaningful unit, like kilogram carbon per square meter per year, whatever. And the next question is, how could one relate such a quantity to environmental drivers? For instance, drought. So drought usually occurs at very short timescales, like weeks or months, or maybe a single year. So we were looking for a variable that is somehow sensitive so that we can also model short-term changes in forest vegetation as a response to drought. And also over long time series so that you get repeated observations. And the product that we are using and that we are investigating is this MODIS 17A3 and A2, which is somehow a combined product from different remotely sensed products, but also from biophysical or biome-specific lookup tables. So I just show you here the very brief overview of how net primary productivity is calculated in the MODIS algorithm. So you have this first part over here, which is the daily gross productivity. And here you have one key parameter, which is this epsilon max and the normal epsilon, which is the light use efficiency. So it says somehow how much of the light that is coming in can be used for gathering carbon by plants. And then we have this big block here, which is maintenance respiration. Because when we want to calculate net primary productivity, we have to somehow subtract everything that is used for maintenance respiration, so that we get like an overall balance in the end. Okay, and all these blocks that I marked here with red is data that comes either from other Modis products or from these biome-specific lookup tables. Okay. And then in the end, we have this block here, which is simply somehow the sum of this daily gross productivity from photosynthesis minus maintenance respiration. And this is summed up over the whole year, so that you get in the end like an annual net primary productivity for each 500 meter grid cell. Okay, and this is the data that we use. And these biome-specific lookup tables, here's a little table where I show you some of the biomes. So for instance, this evergreen needle forest, evergreen broadleaf forest, and just for comparison, what you see is that some of the parameters are the same regardless of the biome, but others are very specific. So what I already said is this epsilon, this key parameter, of course, is different because it makes a difference if it's a conifer forest or broadleaf forest for the light use efficiency. You see here the differences that you see, they may seem to be marginal, but you have to imagine that everything needs to be like multiplicated with 365, because in the end you get a balance over the whole year. And then of course it makes a difference if it's a pure needle-leaf forest or a pure broadleaf forest or mixed forest or whatever. And some other parameter like this Q10, this is the same for each type of biome. It doesn't change. And then you have here this minimum temperature, minimum and maximum vapor pressure deficit. These values somehow determine when the stomata closes or open, so that the trees can gather more carbon. And in the whole Modis hierarchy, you can see that annual NPP is somehow, let's say, the endpoint of a cascade of different products. So of course, the raw surface reflectances are involved. Then you have these land cover maps, of course, which say, well, this is a needle-leaf forest, this is a broadleaf forest, so you have to change the parameter. Then you have leaf area index and photosynthetically active radiation and so on. And in the end, this all somehow goes into this product. Then there's a derivative of the raw Modis data, which is Modis Euro, which we're also using in our project. And Modis Euro is basically the same algorithm than the regular Modis algorithm, but the difference is that the producers used spatially downscaled climate data, in particular temperature. And this makes a huge difference because they compared both their downscaled Modis product and the raw Modis product against productivity estimates from national forest inventories. Okay, so like somehow if you want ground truth. And what they found is that the downscaled Modis product had a smaller deviation from the inventory data than the raw Modis product. It was like 7% deviation versus 23 on average, which is a lot. Anyway, this Modis Euro is currently available from 2000 to 2012. It's not sure whether or not it will be updated or not, but we will certainly in our project compare both products for a certain overlapping period in order to see does it make a difference or does it make no difference. Yes, then I show you the results of a little student project that we carried out a few months ago, pretty much when we started the project. So we somehow compiled the annual NPP for the period 2000 to 2019 over whole Europe as a big raster file. And then we asked a student to pick some locations on this map, extract the data, and correlate it with environmental drivers. And as an environmental driver, we use soil moisture index anomaly, which is a drought indicator, also from a remotely sensed resource, similar to, for instance, this standardized precipitation index or standardized precipitation evapotranspiration index. So it relates somehow deviations to a long-term mean, okay, and therefore it's expressed in standard deviations. If you have a huge negative standard deviation, it means that soil moisture is, or there's less moisture in the soil compared to long-term mean. If you have a positive standard deviation, it means that there's more moisture in the soil than on average. And we wanted to test this just for a few points in the first view, because we wanted to see if the correlations make sense at all or not. So what you see here is actually this yellow bars is soil moisture anomaly expressed in standard deviations, and then this gray line here is this Modi's net primary productivity. And then you see for each of these subplots you see two numbers. In the first number is the correlation between Modi's net primary productivity and soil moisture anomaly calculated over the entire year, so including all months from January to December. And the second number, we correlated the Modi's net primary productivity only for summer months soil moisture anomaly index from April to August, because the hypothesis is that, well, most of the trees somehow rest during the winter, so it's probably not that important if you have like a severe anomaly in December or January compared to the season where trees actively grow, like from May, June, or July. Okay. And what you see is for 5 out of 6 locations, the correlation is positive, which somehow what somebody would expect is that more moisture in the soil determines higher productivity, and less moisture in the soil determines like decline in productivity. Only for this Finnish site here, it was the other way around. Which is interesting because it basically means that, well, these trees grow better when there's less moisture in the soil. It sounds a little bit odd in the first review, but I think for all people that live in the Baltic states, probably somehow understand that, you know, when you think of all these forest stands in Estonia, where ditches are necessary in order to enhance productivity. So it could be that over the long time period, these stands were on average less productive because they were situated in a very moist environment, which inhibited tree growth, and therefore in dry years trees grew a little bit better. But what you see here is this is 2018, this bar, and 19. So this stand was suffering of 2 really dry years. And you see in the 18 years, exactly what happened is that productivity increased a little bit, but then it also dropped down. So this is not what you cannot say that, well, if it's getting dry in the north, actually this will enhance tree growth. It will not. Maybe it will on average a little bit, but if this is occurring more frequently in the future, productivity will certainly go down. Okay. And what you see also is that the second number is in, I think, in 5 out of 6 cases, it is higher, which means that indeed, if you reduce the data to the summer months only, you get a better correlation. Okay, which makes also sense. So the winter months, it's not that the winter months are not important at all, but I think the moisture during the summer months is simply more important. That's why you get higher numbers here. Okay, so this was already part one. So quite quickly, because we are still busy with cleaning the data and gathering other variables. So I just wanted to show you one illustrative example of how you could use this data. In our case, we will do it a little bit more different, because this soil moisture anomaly here comes with 5 kilometer resolution, and we are calculating drought indicator on our own with 1 kilometer resolution. This will still absorb some time because this is a massive amount of data, and then we will also relate these productivity declines to short-term fluctuations and see, well, actually, at what kind of standard deviation do productivity declines mostly occur? So what can we say about tree growth in Europe? What kind of threshold is necessary to really drop productivity down for European forests? Then a little bit about mortality. I think this I will outline a bit more in detail. As you may know, mortality is currently a hot topic in climate change related disturbance ecology. The reason is that during the last years there occurred worldwide more really extreme summer droughts, and in particular in Central Europe and Southern Europe, large-scale tree dieback occurred in the last years. Okay, so this is a very sensitive topic, not just in science but also in the public, because forests have multiple functions, not just for forest production or wood production, but also for recreation and so on. And the last report on forest health in Germany actually predicted that the forest landscape in Germany will change a lot in the last years, and therefore the government decided to put several, I think even $1 billion in resilience research in forestry related research. So there's actually a lot going on at the moment, but the problem is really that quantifications at continental scale from remotely sensed resources are still difficult. Okay, has several reasons, because usually you need object-oriented remote sensing in order to make really statements about how many trees on how many hectares have died in 1 year. So I think there's still need for ground-based gathered data in order to make really reliable statements. And the next point is that, of course, usually ecologists want to analyze long timescales, but then often it's the problem that the timescales that you get from remotely sensed resources are still too short. Okay, and therefore it's somehow difficult when you want really to model something. It's often the case that you end up with too less data. Okay, and yeah, one very valuable resource that one could use is this Icp Forest Network, which was launched in 1985. And the reason was that maybe you remember that in the 80s this forest decline appeared in Europe, which was mainly related to these power plants in Eastern Europe, which produced a lot of emissions, and these emissions damaged the forest. So they wanted to install a long-term monitoring system in order to monitor these crown defoliation and some other things as well. And there are level 1 and level 2 plots. I will talk only about this level 1 monitoring plots. There are currently nearly 6,000 of these plots on a regular 16 by 16 kilometer grid. And 42 countries are currently participating in gathering data. And this is how ICP is organized, a little bit like, yeah, so they have like their own constitution. You can consider them as some kind of a little own state or something like this. The headquarters in Germany, in Eberswalde. Also, when you request data, you have to request the data here. Usually, so everybody can request for data, level 1 and level 2 data. You have to fill out like a request form and send it. And then this request form is sent to all member countries, and all have to agree, actually. This takes usually a few weeks, sometimes a few months, then you get the reply, and you have to give a little project explanation as well. And usually nobody is making any restrictions. So in my case, only Switzerland made some restrictions, because they said that for every work that is going to be published, they want to be included as co-authors, while all the other countries said, well, you can just go on with the data. And usually the data that you get is older than 2 years. So you don't get, the survey is carried on an annual basis, I have to say. Okay, so all the plots are revisited each year, which of course results in a huge amount of data. But usually, I don't know what is the reason for this exactly. I think it's somehow related to the fact that the member states somehow want to possess the right to analyze the latest data on their own somehow. But usually you only get data that is older than 2 years. In our case, we circumvented that problem a little bit, because we included these 2 of the expert panels. This one, the crown condition and damage cause, and also forest growth. So we included the experts in our analysis, and by doing this, we made it a so-called internal application. And if you are involved in an internal application, you get all the data, also like for the very last year. So in our case, also 2020. So this is how ICP usually works. And yeah, this is here. I show you the data that we are analyzing at the moment. So this black layer here is actually is Modi's net primary productivity, and I just overlaid it with the ICP forest plots actually. And in our case, so I looked it up. If I multiply number of plots with the number of trees and number of years we have observations for, in total we get a little bit more than 6 million observations that we have to analyze. And for each plot you get a lot of information. I just here picked some of the information that you get. Of course, you get the tree species, you have the coordinates of the plot, you have the plot size, you have the social class of the tree, the humus type, water availability, the forest type, management history, the mean age, damage cause, and many, many more. So this is a lot of data, actually. The only thing you have to be aware of if you want to use this data is, so this data isn't really cleaned, okay? So the data is provided by each member state each year. They have a certain deadline in the year. I think somehow by end of February, they have to deliver the data for the previous year. And what you get is huge Excel file or CSV files, and then you can start. But be aware that there are still many mistakes in the database, and you need to be a little bit, let's say, skilled in programming, because first, this data is huge, so it's can take a while until you process these data. But also, yeah, somehow, so you don't get any cleaned data or clean products or whatever. What you get is raw observations, and what you make out of it is certainly your own business, okay? And therefore, I'm spending a lot of time since months already just to organize this data in a way that I can be sure that all errors are erased actually, and so on and so forth. So this is quite, in particular, if you deal with all the data, okay? So 6 million observations is not a little, it's not a little task. Yes, and what I want to show you is a quick and illustrative example of how this data could be utilized. And I said in the beginning that I'm talking about this prominent tree disease, which is ash dieback. So just a few words, maybe I'm quite sure that most of you have already heard of ash dieback. It's a fungus, actually, that entered Europe in the early 1990s, and which is affecting our European ash. This fungus is naturally associated with the Asian sister species of ash, with Fraxinus manturica. And Fraxinus manturica and ash dieback somehow evolved, let's say, in a mutual way. Okay, so this pathosystem has evolved over I guess millions of years, which means that the fungus is attacking the tree. The tree developed defense mechanisms, and therefore they are striking each other, but somehow with a balanced nature. Okay, so like many of the natural pathosystems that we know from our tree species. The problem is that our European ash tree doesn't have any defense mechanisms against ash dieback, and therefore ash dieback is actually rapidly killing ash trees. So the usual way is that the crown gets defoliated within some years, and then at some point you see here the fungus causes also wood decay. And at some point, most of the trees fall, not so much because of ash dieback, but because of armillaria fungi that enter the damaged tree and cause these root rot. And then the tree loses all of its, let's say, power to hold within the soil and just falls even at small winds. So in my forest, so these two pictures here are from my own forest actually. I had a lot of beautiful ash trees in my forest, and now actually last year the last one has died. So now they are all gone. And the reason why we analyzed this tree species already is that, as I said in the beginning, we are dealing with drought in our project. Not so much with fungi, but we realized that we need to exclude ash from this data because most of the mortality in ash is not related to climate, it's related to the fungi. So we had to exclude this data anyhow in the beginning, but then we thought, well, it's a rather small data set, so maybe just use it in order to test all of our codes, if they work or if they not work, and if they have some weaknesses. And then if everything is working, we can make a little nice publication and start already. So, yes, as I said, these, for instance, in the British Isles, they estimated that ash dieback will cause total costs of more than 50 billion pounds actually, which is a lot. And the motivation to start with this data was, as I said, so large parts of Europe already affected. There's no detailed information on current defoliation status and survival at European scale. So some single countries also used national forest inventory data, but this is like in like very mosaic data, so every country is reporting a little bit. Then the national forest inventories from country to country vary a little bit. And we thought, well, you know, it would be nice to have a European overview with a consistent survey data, actually. And this could also be used for, you know, like forecasting, actually, and also to inform conservationists, actually, at European level, where are currently hotspots of mortality, and where can we expect, actually, that future mortality will occur. So this is the network of plots where at least one ash tree occurred since 1987. And I have to say that it's not completely correct, because some of these eastern countries here, they joined the network a little later, okay? Which means that in the very early period, beginning 1987, we had mainly plot data here. And then after the 1990s, many of these plots here joined. But this is the actual, so this is the latest data from 2020, is this assembly of monitoring plots. And now I would like to change just for a minute to my, and share my screen, because I show you some data directly in GIS, because it's easier. So I hope this works now. I share my screen. And I would like to show this one. I hope you see this map of Europe. If not, maybe just immediately stop me. But I hope you can see it. So what you see is a map of Europe. And here you see this onion diagram, which shows you the mortality frequency. Okay, so for instance, this little circle here means that, well, in this location, there's like 20% mortality and so on, okay? And what I did is I compiled the data in a way that you can follow up the mortality patterns in 10-year steps, okay? So the first period ends 1990, then the second period is from 90 to 2010, from 90 to 2000, from 2000 to 2010, and from 2010 to 2020, okay? So until 1990, there was no mortality, actually, okay? So nothing, everything was fine, which is somehow clear because the fungi entered Europe in 1992, somewhere in eastern Poland. Before, nothing was wrong, okay? So then until the year 2000, what you see is that we had some mortality here in the southwest, a little bit in northern Italy and France. This was certainly not related to ash dieback, because ash dieback did not occur in this area. Okay, so it started somewhere from here and then spread westwards. So this mortality of ash dieback is certainly related to other reasons, like climate. But what you see is that until the year 2000, there was already large mortality taking place here in Belarus, actually. So this is an event where all ash trees have died. But then 10 years later, 2010, you see that more plots are popping up, and they are popping up mainly in this region, which is a very good hint that it is related to ash dieback. And these occur mainly in Lithuania and in Poland, and also already in southern Scandinavia, okay? But still, I would say not dramatically, okay? But then just look what happened in the last 10 years. So what I show you now is the last 10-year period until 2020, so until last year. So what you see is, especially in southern Scandinavia, we have plots, a lot of plots where all ash trees, this is 100% mortality, so all ash trees in these plots have already died. And we have other spots popping up across entire Europe, okay? And this is actually what is exactly thought at the moment, that the disease is especially in the last 10 years, it has accelerated a lot, and also reached the British Isles and even Ireland. So I can just show you, in Ireland we don't have observed mortality in ICP plots, but I can show you the defoliation status up to 2020. So this is now the average defoliation per plot, and you see that already in Ireland there are some plots where we have like between 60 and 80% defoliation, so we can expect that some mortality will occur as well in the very next years. Okay, so this was just to show you how you can visualize this kind of data quickly. And now I stop sharing my screen and come back to the presentation. Okay. Yes, and then you can like break the data down into the single countries, which I show you here. So here you see the mean defoliation per plot and how it developed from the 1990s until today. And I marked all countries where we found a significant increasing trend in defoliation here with red. And this fits really into the pattern, is that mainly in the northeastern states and southern Scandinavia, we see a very clear increasing trend in defoliation. While in some other countries, the trend is non-significant, like for instance for Belgium or also for Italy. So there, the disease, it is already observed to be there, but the time from entering Europe until getting there actually was still too short to result in very heavy damages. But nevertheless, what you see here, in these countries, it's very severe actually, the pattern. And yeah, I have to say this as well. Sometimes you see this kind of peaks here. So the peak is very high, and then it goes down. It doesn't mean that these plots are somehow recovering. It simply means that usually at this peak, a lot of mortality is occurring at one at the same time. And then, of course, these trees are going out of the survey, which means that when you calculate average defoliation, the average defoliation will be smaller after the trees have been removed from the survey. Okay, it doesn't mean that the plots somehow recover. So what you can do as well with this data is you can calculate survival probabilities and survival functions. And we use this Kaplan-Meier survival function, which is quite sophisticated because it takes into account the right-censored data of nature of the data. In this case, our data is right-censored because, so how should I explain this? So for instance, when you carry out a COVID-19 survey with patients, and you begin the survey at some certain time, and you want to know how long does it take until patients die because of COVID-19. It's usually the case that when you stop your survey at a certain point, not all of the subjects that you're investigating will be dead, and therefore the data is right censored. Okay, and this is in our case, of course, it's the same. It's the same problem. So by 2020, when I got the last data, which I included, many trees were still under risk, but they are not dead. Okay, so we had to use a survival function which is taking into account this right censored data, and this Kaplan-Meier survival function is doing this very well. And what you see here are these two graphs. These are so-called step functions, where you see how survival or mortality has been evolving since the beginning of the survey. Okay, but you see this time point 0 is actually when the survey data started, and here after I think it's now 28 years, you can see what this overall survival probability is in ASH. And you see we calculated two graphs, this black one and this red one, and because we wanted to take into account that you know, not all ash trees in Europe have been infected from the very first day when ash dieback have entered Europe. So it entered Europe here. As this map here, you can see the dates where the first observations of ash dieback were made in Europe. Okay, so of course it entered here, Poland and Lithuania, much earlier compared to France, Germany, or Italy. Okay. In the first survival function, we treated the data in a way that we said, well, we just say 1992 was the day of infection, regardless of whether the trees were located in the west or in the east. And the red function takes into account this spreading history of the fungi. Okay, so. And this makes a difference because you calculate the time between infection and death, okay? But the problem is when you don't take into account that the fungi needed some time to get from here to here, it would mean that the survival times of these trees would be much, much longer, and therefore the survival probability would be much higher. And this is exactly the case. So you see, after 28 years of infection, of course, under the let's say hypothesis that the fungi needed some time in order to get to the Western countries, of course, the survival time is much lower because they were infected much later. Okay, so and it's just I'm just showing this to demonstrate that these kind of data need to be taken into account as well, because otherwise you end up with a very biased survival probability. In the first case, one would assume, well, the overall survival probability is 0.8 after 30 years, which is not that dramatic actually. But the truth is, it isn't. It is 0.5 after 3 decades of infection, and this makes a huge difference. And yeah, as I said, actually, forecasting is quite an important thing, in particular at European scale, because like conservationists and also policymakers, they want to know how much time is left. So how much time do we have for actions actually? And we just made a simple forecast. So this black line here until this gray vertical line is the currently observed mean defoliation per plot. Okay, so you see it's taking into account all the member countries, and you see there's a very significant trend, increasing trend, and then from this time point 2020 we simply forecasted it into the future with 2 different models. So one we used this exponential smoothing, and the second one we used is this ARIMA forecast. It's a little bit more sophisticated, but also more complicated in choosing the right parameters. But what you see, interestingly, is until this critical point here, like where the stands would on average reach 50% defoliation, both models largely agree. So this is somehow until 2000, I think, I don't know the right number, but I think it's somehow 2030, which is not much. It's 9 years from now actually. Stands will reach most likely critical point where trees have to live with 50% of their leaf area somehow. And I think this is something that you can also easily communicate to conservationists and also to policymakers and stakeholders, that you say, well, 9 years from now, according to the survey data at European scale, 9 years from now, stands will reach a critical point actually. So somehow we have to act at European level in order to set up new management schemes or conservation schemes or whatever. Yes, and then finally, of course, what one could easily ask is, well, how do you know actually that all of the mortality that you observed in the plots is due to ash dieback? So trees are dying around the globe everywhere because of drought, because of thunderstorms, because of bark beetles. So how can you be sure actually that all the mortality that you saw is due to ash dieback. Well, we can't be sure, and in some cases the damage cause is assessed as well. So in many cases we saw in the data that ash dieback is the driving factor for the defoliation, and others are not, because you have to imagine that the disease, even until the early 2000 years, the disease was not known, not even by experts. So they just saw a defoliated crown and were not able to assess the really scientific cause for it. But what you can compare easily from the data is you can compare ash dieback, so the mortality of ash trees, to the background mortality. Okay, so you calculate background mortality for all the remaining trees in the same plots, and then you can, for instance, make a very simple line plot as here, and then you can see, well, are they somehow correlated, or are they not correlated? In this case, you see, so this red line is the background mortality. Background mortality was, in most of the years, was even higher until, let's say, 2010, which is somehow clear because all the other trees in the plots, of course, are larger in numbers. So it's somehow clear that the mortality should be higher. But then what you see is the first thing you can see from this plot is that there's not much of a correlation between background mortality and ash dieback, which is a very first good hint, actually, that the predominant reason of dying is ash dieback in ash trees. Only here in the 90 years you see actually correlation. This was the plots that I showed you early on the map in southern Spain. So this very early mortality pattern was certainly not caused by ash dieback, but by climate-related factors. But then since 2010, you see that ash dieback has largely accelerated, while the background mortality in the same plots somehow stood constant. And when you compare the overall mortality rate, simply expressed as the number of trees that have died compared to all trees, you see that ash dieback is much higher than background mortality in the same plots. Okay, so that means we can be quite sure that the predominant reason for mortality in ash trees is ash dieback, in particular within the very last 10 years. And that's it. I hope it was somehow interesting. It was a little bit a mixture of everything. But yes, if you have questions, I'm happy to answer.